Fine. So, I do hope everyone is doing well. Good morning. Yeah. So, today, if you remember from yesterday's class, I had said that we'll have Sundays for quizzes and things like that. And I've also shared a tentative timetable with everyone. I hope you have you have access to it through Google Classroom. So keeping in mind that kind of a timetable, today I'll be teaching. I won't call this teaching, but kind of trying to instruct a little on the remaining part of passive learning under reinforcement learning. And then from around 9:05 to 9:15, I'll have a quiz. I'll put it up on Google Classroom. So you have about 10 to 15 minutes to solve it. And you'll get another 10-15 minutes to upload it. So during that time, if you have any questions or anything, any queries, we can have that on Google Classroom. Okay, since that will be the platform everyone will be shifting to for the quiz, so we could have it over there. Fine. Or we could also have it over email. We could do anything. Very well. So, without any further delay, I'll start the class for today. I'll share my screen. Oh, before I begin, does anyone have any, excuse me, queries or any observations from yesterday's class? Were there any observations like you were able to relate something that was done in class with what you do in real? Was anyone able to do that? If I share, I was just thinking about it, about the kind of policies. Since this is passive learning and we have a policy that is a kind of a rule in a way that is fixed. Right. So now we don't know what these rules mean, but we're just trying to find out which rules are good enough for us to live in the world. So now, if I try to draw an analogy with this, the way babies learn, then if we say that evolution has gifted child the right to cry when it is in danger or when it is feeling threatened or when it has a problem, right? So now it just cries, and there are a number of rewards that it gets after it cries. Some immediate caregiver. Right, I'll try to do that. Some immediate caregiver comes down and tries to comfort it. So there is this thing, there's this policy that it has to cry when it is in danger, but there is no fixed goal happening out there. And for us at the receiving end, elders or the immediate caregivers at the receiving end, they eventually learn the pattern. So here it's this mix of reinforcement learning happening for the child in one way. There is a reinforcement learning happening for the caregivers in one way. So coming to that example of that question in class about supervised, unsupervised, and reinforcement learning happening in sync in real world, that is exactly what happens. You are gifted some policies because of evolution, and then you learn through repeated sampling. You can learn through just immediate rewards. You can learn through long-term rewards. Long-term rewards come in when we grow slightly older, when we move on to the realms of deliberative and reflective thinking. deliberative policies are those, or deliberative schemes or strategies of learning, where I have a number of uh, solution strategies and I try to find out which one is the better one. And reflective is when I try to figure out if the one that I took is good or not, or how good it is, or should I have had done something better, or can I improve upon it? Right. So this is something that we keep juggling through a deliberation and a reflection. I haven't shared a presentation. I haven't shared yet. This is just what I'm trying to kind of recapitulate from yesterday's class and kind of giving you a feel of things. So I suppose this makes sense, isn't it? This constant juggling that we do in order to kind of sustain ourselves in the world that we live in. So now, if we are trying to design an intelligent agent that will function, if not as well as living beings do, but pretty good enough, then it has to have these kind of mechanisms to get along. In supervised learning, what it does is you have a large number of label samples, you have exact matchings, you have classes, you have categories, and it just tries to learn patterns from these label data. In unsupervised learning, you again have unlabeled data and you try to figure out patterns from it. But in reinforcement learning, it's finding out the unlabeled data on your own. In a way, the unlabeled data as well as the rules, you try to just find it out on your own. So it kind of takes this to the next step. And here we have a mix of deliberative and reflective learning happening at the same time, if everyone's got that. So now moving on to the presentation, I'll share my screen. Yeah. So right. So this is where we had stopped yesterday. I had shared this example with everyone. Excuse me. I had shared this example with everyone where we see these values getting updated iteratively using the direct utility estimation, which is basically you do a large number of samples and you take an average of them and then you try to find out which one is making sense. Okay. So now the problem with the direct utility, sorry, right. So now the problem with direct utility estimation was that we were not keeping track of the state semantics or the state connections that are meaningful. We were absolutely having no clue as to why some values were more, why some values were less, and what was happening, because there was no kind of evaluation happening. Right? This kind of policy that I have been given, since it's a passive mechanism, I have a fixed policy. I don't know what it means. Right. So I just try out different things. I try them a large number of times just to make sense, but I'm not keeping track of the meanings of these connections. So in some ways a direct utility estimation is fine when I'm not concerned about what these meanings actually are. Maybe it's a good thing to do when when the machine is at the very preliminary stages of learning. But once it has to move into a more complex world, right? It has a lot more, the horizon is a lot bigger, then perhaps keeping track of the state semantics is important. Right? So, so then we come up to this kind of an equation over here that everyone can see, which kind of takes the reward that the state has which is if I'm in S, I have an idea of what the reward my state already gives me. This reward that I've calculated from all my previous examples, all my previous iterations, my previous visits to my state, or something that I have just begun with. I'll be showing this to you, and then I try to plug in over here an estimate of the utility of the successor states. So this, in a way, I am plugging in something that I have learned into my utility function, right? So this is a more adaptive way of doing things, right? Where I try to kind of utilize what I have learned earlier or what I have an estimation of from my previous experiences. I try to plug that into my learning algorithm. Fine. So under this, we have different kinds of strategies that come under this adaptive scheme of things. And for this class, we'll be doing adaptive dynamic programming and a temporal difference mechanism. So if you remember, yesterday I had given a short brief on what dynamic programming is. What we do is if you're given a big problem, you can break it into sub problems such that these solutions are recurrent in a way that you keep utilizing these solutions. If again I want to draw an analogy, I think I had given the example yesterday itself, is these neuronal connections that you build up. Or maybe, for example, see you're trying to find out a way to traverse from your home to your institute or to your organization. So you have a set of buses or a set of vehicles that you take, right? So now, if you know the costs of these vehicles or the distance that these vehicles take, so you can prepare a tabulation of these individual distances. In the very first case, in the first day that you are traveling, you just update what you have come to know. And then you do that on a regular basis, meaning that today you took, say, bus A, and then you took an auto B to reach destination. So then you you do a complex calculation of the cost and the time it took you. So the next day you take bus A, then auto D, which say is a slightly divergent or a slightly different route, but it leads you to the same destination. So then you try that. So then what happens is you can update your costs backwards. So you take a step forward, you look ahead a little, you have utilized that same information that you had, that bus A costs this, right? Perhaps you have utilized that cost. You have it in your in the table that you have in your mind, and you have tried out something else. So starting from your source or the start step to your destination, you have two different paths or two different successors coming in, which is S dash, different successors coming in, and you try to plug in what you have learned, these new successor information, as well as what you already know about the immediate successor information into your learning algorithm. And then you try to figure out which one makes more sense. So in your case, the reward would be where the time is less as well as the cost is less, right? So now at different points in time, this could be different. You have a lot of time in hand, you might want to explore, or those are again very complicated cases, right? So for this particular class where we are talking about passive learning, you have these policies fixed. There's a bus and an auto. You have maybe two different ways of doing it, and you're just trying to find out which one makes more sense. Okay. So now this is what adaptive dynamic programming is, because you are utilizing recurrent values, values that keep appearing, you do them. And in temporal difference, the difference actually between adaptive dynamic programming and temporal differences, the dynamic programming or the ADP strategy is more of a global mechanism that is happening. in the sense that if I update any one of my successors, I kind of back propagate across all my different or all the different states that lead to S dash. For example, S dash is my successor state or my current state, and my series um, of source steps to S dash was S. So then I keep updating this backwards, right? For my entire grid or for my entire table that I'm trying to learn or this entire model that I'm trying to learn. But in temporal difference, it's only about the immediate successors. So, in one way, temporal difference is more of a first approximation of the ADP strategy. ADP, do keep this in mind. I will be showing you examples as well. In ADP, it's more about the entire table, the entire model. That is what I'm trying to learn. And in temporal difference, it's learning these immediate semantics, the immediate rewards, and trying eventually to learn the entire model. Eventually. Okay, that is what is happening. So if I move on now, this is the algorithm. Sorry, there is a question. Question is always additive, or it can be the reward function can be different. It doesn't matter. It can be additive, it can be multiplicative. It all depends. Depends on what if you have a particular reward function that is fixed for you, you can utilize that, right? And in certain cases, if it's not fixed for you, the easiest scheme is to add on, which is like a reward to go kind of a principle. You kind of add on the rewards. That is an easy way to do things. And it can be actually multiplicative when you try to do something more random in nature, something more stochastic in nature. The additive policy actually counts for something that is more deterministic. And the multiplicative strategy, where usually I can give you these examples, since this is the one that's just coming to my mind. Multiplicative strategy is when you have probabilities coming in, when you have a more random thing to explore, a more random environment to explore. So you could think about multiplying probabilities of, uh, of your visits, or probabilities or frequencies of your visits. Like in this particular example over here, they estimate the probability as a function of the frequency of visits. Okay, I'll be giving an example. So it could be additive, it may be a deterministic fashion, a very simple way. It could be multiplicative if I'm trying to do, if I know my function or I have probabilities coming in. And the next question, adaptive learns from the best choice available to the agent. In a way, perhaps we can maybe say that it tries to learn from the best choice available. Best choice over here is again a function of what it already has done. Since over here in dynamic learning or in dynamic programming, my purpose is to reuse solutions. So I will particularly try to explore choices that I have already visited um, or I have kind of made for myself. For example, say this traversal that I said from the source to your destination. If you have only been using the bus and the auto rickshaw, example that you are not a very intelligent agent out there, and you just have this policy given to you. I'll come to that. You just kind of you just have the choices available to you. You are not going to maybe explore anything beyond this. So there is a problem with dynamic programming over here is we might not be if I have a very fixed policy given to me or just a set of choices available, I might just be restricting myself to one thing. And if that particular restriction does not kind of embed into my learning complexities of the world, right? For example, in the book, they have given this lovely example of you learn that if I traverse a certain route, I have to um, kind of the signal never comes, right? So you learn that. So then what happens is maybe you never train that a signal could ever come, and then eventually maybe you just skip until again another reward happens with a negative function coming in, that if I skip a signal, the policeman gives me a ticket. So what happens is you are using things over there, because it's over here, the state dynamic, it does not take everything into consideration. The state semantics, it's a very restrictive environment over here with just the choices that I have just visited. So this complex environment of what this traffic signal actually means, that may not have ever been embedded in my learning module. Right. So then first few cases again I'll have some errors coming up and then I will eventually learn. But then what is happening over here is these certain tricks maybe it makes sense as well to kind of go beyond dynamic programming at times. It does. So over here, what I would like to tell everyone is it, it these mechanisms are just some tools in order to explore what reinforcement learning is. But actually, we do a mix of things in real. And if we have to have an intelligent agent that is functional in the real world, it has to do a mix of everything. It just can't be doing adaptive dynamic programming, or it just can't be doing direct utility estimation. It has to do a good mix of everything and eventually update its rule base, eventually update its knowledge base, and so on. In case of in case of multiplicative probability, it will be diminishing in nature. It will be diminishing in nature depending on certain factors, maybe. For example, if my probability derives from the frequency of visits, right, so the probability is going to go up, isn't it? But again, if I have, like in temporal learning, maybe if I use a function, a multiplicative function that is inversely proportional to the frequencies, then it's going to be diminishing in the sense that since I've kept visiting this particular link or this particular experience, I've learned pretty much what I have to learn from it. Right. So there are different ways of visualizing things and actually making things fit your purpose. The entire schematic or this entire all these tools, they just right. But then over here, the probability could increase. That is what I mean to say. For example, if you start, the more you visit, your probability of visiting that increases. So in that perspective, it is less than 1, right? But between 0 and 1, again, you have a large number of values to traverse, right? It's a countably infinite series over there, sequence of values. So, right. So now, what I'd like to again say over here is in this class, I have been pretty much following Norvik's book, and algorithm is a type of RL. And algorithm, which one? I think I'll need to look this up a bit because is it the ant colony algorithm that you mean to say? This is to Nikhil. Is it the ant colony optimization? Is kind of RL. In the real world, it is. If you're actually trying to model ant colonies in the real world, then there is reinforcement learning happening there, yes. because ants they do follow a path that the other worker ants have established for themselves, but some ants are also curious and then they also diverge. So at times you'll be finding one ant doing a lot of iterations to try to find out which one is the best route. So now depending using the dynamic table or the programming scheme that this worker ant has done, all the other ants start following that particular scheme. But then again, maybe another ant comes back after certain other explorations and then the table gets updated. So if you to actually model the ant colony optimization that happens in real, then maybe there is reinforcement learning happening. Yes. Right. Yeah, what I was saying over there, the multiplication of numbers less than 1 reduces the value further, but it's not just the probability that is coming over here, right? You have the probability that is applicable, and you also have the utility that is coming. The utility is going to go up, right? So this is a mix of different strategies that make up the real world essentially. So now, going back to what I was saying, I have been following Norvik's book for class, but there are certain other resources as well that I have been looking into. I shall be sharing them I suppose everyone has access to the updated slides. Here I have put up an example already of a fantastic resource I found, and I'll be putting up the other links, and I would encourage everyone to visit all the resources, so that it kind of helps the reinforcement learning that we are doing in class. This is a kind of reinforcement learning, right? Right. So now going back to the algorithm for adaptive dynamic programming, I'll present my screen. So, so over here, what we do is we try to plug in these frequencies. Just like I was mentioning earlier, you have an idea of the grid world available to you, right? Like these are the certain reward values that I'll get. You have certain if it is a deterministic model of the world, then you have exact schemes or exact kind of traversal mechanisms given out to you. Like from this particular state, I just move in this way to another state. But if you are in a stochastic kind of an environment, then you will have probabilities attached to each kind of movement. Meaning, if you are going from state A to state B, you could have different ways of doing it. So you'll have probabilities attached to each of these paths. So based on this model of the environment, what we do is we add on a series of frequencies of my visiting these states. I'll show you an example, right? So over here, if I have these kind of trials, drawing from the last grid world example that I showed you yesterday. So then over here, starting from 1, 3 and reaching on to 2, 3, the number of the trials are 2 out of 3 occasions, right? So because after 1, 3, I come to 1, 2, and over here from 1, 3, it's a 2, 3, and from 1, 3 again, it's a 2, 3. So out of 3 different trials that I have tried for this particular policy given to me, 2 out of 3 cases, I visit 2, 3. That's the block on a right movement. The policy that I've been using is a right action scheme. So if I utilize this value, I update my table for the successor relationship from 1, 3 to 2, 3. Right, I update my policy for that. I'll go back over here. This frequency, I update my policy over here, my probability, and I then do a policy evaluation. Policy evaluation meaning an iterative number of steps to update all the other successors backwards. Right. If you see the example, if you see the algorithm over here, I have a start state and I have a set of previous states. So I have to update this set of equations for all the previous states that lead to S dash. Right, using what I have just learned, this updated probability over here, this new frequency that has just come in after a new visit. So once I keep doing it, and when I see that my utilities no longer change after a certain number of iterations, and then I step out of my policy evaluation mechanism, and then I move on to the next state or the next set of states. If S dash is already a terminal state, I don't have much more to do. I already have a policy idea developed in front of me. But if it isn't a terminal state, then again I restart my algorithm. So the dynamic programming mechanism that is coming up over here is reusing these frequencies over here. Right. I have a frequency that I am keeping stock of my visits and I increment them in order to update my learning module. Okay. Actually, for policy evaluation over here, you can do two things, right? You can use a value or you can use a value action pair. Depending on what you have with you, depending on the model that you have already with you, you can do value iteration, solely value iteration where you're just updating the values available. Since this is passive learning, a value iteration scheme makes sense. Or maybe you start with value iteration because my policy is fixed and then move on to policy updation in over time. You could do a value action, a value function, or a value action pair. For this particular example that is there in the book, this is what they are doing in policy evaluation. But there are other examples where they do a lot more complicated things. I'll be sharing those resources with everyone, actually. So now, if I come out from this screen, there was this another example over here, right? Over here, this particular example, they use a stochastic model of things. They use a stochastic value function model over here, and they update their table iteratively. They have a random policy, and they keep updating the table. I have shared a reference from where this has been taken actually. This is the other textbook, which is in the resources file. So you can have a value function update, and you also, since this is a passive strategy, a policy update is a policy improvement is not something that we are actually looking for. A value or just the utilities, that is what we are concerned about since this is passive learning. But once the adaptive dynamic programming, in fact we will be doing it as well. The minute we take policy improvement into consideration, we have a policy update happening as well. So in this particular stage, it's all about policy evaluation, kind of just updating the entire grids over here. Right, it's just about that. This is the same example. Right. Again, this is another example where they look at the probabilities of 1 to 1 leading 1 to 2. And here it's again 2 out of 3, so they update. So this strategy of utilizing the frequencies is kind of expanding the direct estimation method towards dynamic programming. Right. So as in direct estimation, you were doing multiple samples. So over here, it's not just samples, it's more about the semantics that are coming up into consideration, meaning from one state to the next state. If I go back to my screen over here, if you see the function, This involves relations of S and S dash, while in direct estimation it was only about the S's, the current states. Fine. So this is what is happening. I update my probabilities, I do a policy evaluation, I update it, and then I move on. But if for an active reinforcement learning scheme, I would have a policy improvement step over here as well, where I kind of evaluate which mechanism or which route gave me the policy. Right? So this is what I've been saying. So now what happens over here is the policy derives from the estimated model, the model that I have of the world around me, and it only looks into paths that I have taken, into those actions that I have actually been following. It doesn't. It's global in that perspective, in with the perspective of that particular policy, right? Or that particular what should I say, the particular environment that I have been traversing keeps modulating or iterating across that. But it doesn't take the entire global picture into perspective. Okay. So for that global picture, there are these mechanisms of Bayesian reinforcement learning. There are robust control theory mechanisms where they have estimates of world models and they try to find out the one which gives you the best performance amongst these world models. So these take the adaptive dynamic programming policy to the next level, Bayesian reinforcement and robust control theory. If there is time, maybe I could talk a little more about these in the next classes. I shall try doing that. But the problem over here is it could become restrictive in nature. If you think about the example that if I've told you that bus 232 and the auto, and maybe bus 232 and auto B, these are just some rules that you have to follow. But there could be other buses that could lead you to better directions, but you never explore that maybe. So in temporal dynamic programming, what we do, this temporal dynamic programming in a way is not far better than dynamic programming itself. Temporal learning, sorry, is not very much better than dynamic programming. It's more like a first approximation. But what the intention of temporal dynamic programming is, let's update these immediate state and successor values instead of updating the entire table. Instead of kind of updating my entire knowledge base, let me just update these immediate relations and then I will eventually come up to learning the entire thing. So in temporal learning, what we have is a learning parameter coming up over here. A learning parameter in the sense, which again is a function of the frequencies, kind of inversely proportional to the frequencies. But here, if you see, I've given a star over here because what is important is not just the frequency of revisits, but the time difference between the last visit and my current state or my current time. In textbooks, you may not find that particular point of looking into the past, in the sense of looking into this time gap between my last visit and my current state. You may not find that example because that I shall write it over here in chat. That is in a paper you will be finding on by Saket Navlakha on distance and time sensitive Bloom filter. This is an article around 2018, I think. Over there, what they do is they just don't use the frequency of revisits, but they also look at the time distance, the time since my last revisit till the current time, because the thing that happens over there is, since temporal learning is all about the time, the number of revisits, if I include this other parameter of the time gap between the last visit and my current time, I also include a certain bit of dynamicity into my learning algorithm, if you think about it. Dynamicity in the sense that once upon a time, I had taken a particular step and I was constantly learning from it, and I have nothing more to learn from it. So it kind of goes back to your memory, it goes back down somewhere. But then again, you revisit it after a long time. After a long time, certain situations allow you to revisit or kind of go back to it again. So then what happens is you again start revisiting. There is a possibility that you start revisiting that particular. I shall come to that question. We can revisit that particular state again, or maybe I just revisit it once. So then over here, the utility of that particular the state action, this new transition that has happened, it should be different, isn't it? I have a history, just to reiterate, I have a history of visiting a particular state. I do that a large number of times, and I have that well embedded in my knowledge base. And my learning parameter is dynamic. The value has come down, which is inversely proportional to the frequency. And I have learned it. I have nothing more to learn. But say you revisit this strategy after a long time. So now when you revisit that strategy, you can either keep revisiting it again, or you may never revisit it. So in that case, the utility function has to be very different, isn't it? If you're trying to build a dynamic reinforcement learning model, it has to be very different. So using the frequency of revisits is the primitive way of doing things, utilizing these distance and time sensitivity. Distance in the sense of the distance between my last visit and my current time, that is something that is a little more dynamic when it comes to learning policies. Okay, you can refer to this reference that I've given you. I could also put a link on the resources for you to visit. It's a very interesting paper. So this is not a Markov decision process. This actually becomes a partially observed Markov decision process, if I may use the term. It actually boils down to that. Okay, because certain things are observable, certain things are not observable. So essentially it is Markovian in the way it is, in the way the scenario is, but then certain things become observable, certain things are not observable because you have never revisited them, they are never in your database, in your knowledge base. So this is more like a partially observed MDP that is happening over here. So the problem, yeah. Sorry. Okay. So this is how it goes. So now the problem, if you see, with dynamic programming and temporal difference learning, at least in the passive case, it's all about policy evaluation. For adaptive ADP, adaptive dynamic programming, it's across the entire state successor table, giving the environment that I have. And in temporal difference, it's only about the successor states. You see, there is no summation function happening over here. So it's just a local equilibrium. It's just a local equilibrium that we are searching for, a local consistency that we are searching for in order to arrive at the global equilibrium. And eventually we arrive at the global equilibrium. We do that eventually through a large number of revisits. So adaptive dynamic programming model is more of a model-based kind of a scheme because you are being given fixed policies, and you know that you have probabilities attached to things if it is a stochastic model, and but you're trying to update your entire table. But in the temporal difference mechanism, this is more of a model-free approach because you don't have the entire table laid out in front of you, but you're just learning the successor relations in order to arrive at a global strategy or at a global equilibrium that is coming up over here. So temporal difference, essentially, if you, to my mind, actually, I would like to know your thoughts on it as well, is somewhere in between a very passive strategy and a very active strategy. It somewhat lies in between. It gives you hints of active RL because you're trying to find out more about the environment, but it also has hints of passivity over there because I have certain policies that are fixed for me. When if I have the policy fixed, actually it is a passive RL. There is an active RL. So this somewhat straddles between these two strategies, the active model and the passive model of reinforcement learning. So this is the evaluation model across successors. Over here, you see this function that has come up. It was there in the earlier slide. This function comes up over here as my mechanism of updating my utilities, and you have a table of frequencies over here. But this is not a recurrent thing that is happening because I'm not going across all the successors or if I'm backwards all my previous states. I'm not doing that. So now difference between reward and utility. Reward is more of a short-term something happening, and a utility has hints of a long-term reward in a way. The drone learning to fly video was an example of that particular was a mixture. The strategy that particular laboratory had used for drone learning, they had used a direct estimation mechanism for it, but it can be adapted to dynamic programming or a mix of both. We can very well do. These are people are building up their own algorithms, right? They are using different strategies. Like I mentioned over there, you have this control mechanism that is over here, this robust control theory. For complex systems like drone learning, they might be using a robust control theory embedded into their reinforcement learning mechanism, where it is more about all kinds of the entire world, different kinds of world models coming up to you, and then you choose which one is the best. We could have something like that. The reward for the states will remain fixed. The reward will you start with a particular reward, right? And then it will the reward will it remain fixed? No, because over here, if you see over here, the if I go back to the last. Right. The RS over here is the observed reward. Right. This is the observed reward over here. So it could change. Like over here, if I show this table to you, the reward values over here, they keep changing. They iterate. So you start with a particular value and then you reiterate, then you keep iterating. The problem with direct estimation was that it is a very fixed strategy. But in dynamic programming, we try to bring in what I have learned, my transitions that I have learned and my observed rewards. Right, so that is where this is a more, as the name suggests, it is a dynamic strategy. For chess playing agent, the reward is given at the end of the game. The utility and reward will be the same. For this thing, I don't think it will always be the same Because it has a set of moves, right? The reward that you get at the end of the game is just one game, right? That is what I was trying to arrive at. When you are trying to learn a game of chess, it's just one game. The end of a game leads you to a checkmate condition. So entire series of moves, this entire sequence of moves can be considered to be one policy. Okay, so when you play another game, you have another policy. We have something. So what happens is when you have a certain number of cases or a certain number of experiences of games that you have played, you keep updating your learning backwards. Like for this particular move, when I had taken this, say, I am in state A, I am in block A, and I take an action B, I have choices. Given my, say, I have two examples or two experiences of playing chess, two games, right? Two different ways of arriving at a winning strategy, say. So if I have from position A, if I move to, or I use action B to go to a new position and I use action C to go to a new position, if B leads me to a winning strategy, if action B leads me to a winning strategy in the end or a quicker winning strategy in the end, my rewards could update. My rewards could be updated. Because what is going to happen is I'm going to revisit B again, maybe C. Right. So this is essentially what I've been trying to point out so far. I absolutely appreciate all the questions that have been coming up, because once you have this chess playing environment, when you have AlphaGo, these kind of environments coming up, the policies are very fixed. Like this is what you do. These are the certain movements of these particular these pieces. The policies are fixed, but there are numerable ways in order. The semantics are numerous. The world is huge, right? So you have your context fixed. You have chess playing fixed. An agent that can play chess will maybe will not be able to play AlphaGo maybe. But then, in a particular environment too, you have to learn which one is an optimal policy, right? Which one will lead me to greater dividends? Dividends could be rewards. I get, say, more sweets in the end, or it could be time. I reach the winning strategy faster. So what happens is I have to update my table. I have to update my knowledge base. But then again, it becomes very pessimistic if I no longer revisit anything. For dynamic programming, there is a tendency that I may not revisit C again. Since I constantly keep visiting, say, the move B and it gives me rich dividends, I may no longer look into other native paths. I may just not be doing that and it dies out. But that perhaps is not always a good case. Perhaps a bit of exploration could lead to new information coming in, new surprise. So over here again, if you think about this AlphaGo game that DeepMind has been, equations are updating. Just you. Sorry. Right. The equations are updating, but see over here, you're observing differently. You're using a table of your transition, right? And you are plugging that into your equation. Ultimately, the utility is getting changed, but again, utility is a function of the reward, right? So you can have your rewards getting updated too, depending on the policies. Yeah. And these are just some, what shall I say, outlines of strategies, and you are allowed to update anything that you wish to. And we do that in real. We update our rewards, we update our strategies, we update our policies, we update our static action pairs. We do all of that in real. We do all of that. These are just some, what shall I say, broad schemes of doing things. And coming back to this AlphaGo example that I did, that I just mentioned over there, at times it is necessary to look at the untrodden paths because it could lead you to rich dividends at times. But then again, the question comes is, when do I look at the untrodden paths? So one strategy for that could be when I'm not learning anything, when my system is in the idle state, I could be doing a bit of improvement thinking. So if you are trying to build an intelligent agent and say at a particular phase it is not doing any learning or any activity, it could actually go through what it has already learned, look at the paths that it hasn't visited in a long time, and then revisit to see what has happened. Because all these strategies that we are using over here, they're not looking at the big picture, the entire world, if you have to think about it. They're not looking at the big picture. They're just looking at these immediate rewards, these immediate things, these immediate kind of a greedy strategy to do things. But being greedy is not always the right way to go about the world. Isn't it? So you are free to design your own policy. You are free to design your own reward function, your own reward updating strategies. This is all a very, very dynamic environment that we are in at the moment. You are allowed to do all of that. And in fact, the more of the dynamics of the real world that you can put into your reinforcement learning algorithms, the more better will the algorithm mimic the real world, and more, what shall I say, an intelligent agent will you be having. In fact, a question that I can think about over here is that is actually coming to my mind. I've even asked this question at the very end of the slide. Is when you are very little, you make mistakes, but people don't scold you. Isn't it? You might be, say, babies use half words, right? Or new words. They coin up new words. But they don't always, they're never reprimanded for it. They are encouraged, lovingly encouraged, but eventually they learn that word. Right. So again, if we could model this complex thing that we learn, that is, you don't always give a negative reward if there is something wrong if something wrong is happening. You don't do that, but you eventually learn in the long term. So those kind of dynamics, real world dynamics, if we can actually plug into our reinforcement algorithms, maybe we will have an excellent an intelligent agent or an excellent learning mechanism coming up for us. And these strategies of looking at untrodden paths, that is where perhaps a spark of creativity comes in. That is what AlphaGo did. This move number 78, I suppose that is what everyone mentions. Move number 78. That is an untrodden path that it took, but it must have been there somewhere amongst all its different of all the training samples that it went through. So it tried it and it won it. But then the human being, the opponent, he perhaps did not expect this to happen, because again, move 78 is not something that pops up in its own knowledge base. Right? The human player's knowledge base wasn't updated with move 78. It never did that. But the The AlphaGo did that. So again, the question over there comes is it was reinforcement learning that was happening over there. It learned from all these game samples that it was fed with, but it took an untrodden path. It perhaps was somewhere in one of the different game samples. It was maybe there. The frequency of revisit was very low for it, but it just tried it. So now the more of this that we can perhaps embed into reinforcement algorithms, treading the untrodden path. Right, you know that there is a path. Let's try it out. If we can model these kind of things into our reinforcement algorithms, look into modeling reasoning. Right, we have state semantics coming up over here, but reasons, proper semantic reasons. If we can actually put that into our reinforcement learning algorithms, maybe we will have better learning strategies, we will have better intelligent agents, maybe better reflective agents. Fine. So this is these are some of the many questions that keep popping up in my mind when it comes to machine learning and reinforcement learning and learning in general. And I would like you to be curious about these questions as well. Curious about how learning happens in nature and how well we can maybe model those so that we arrive at learning strategies, because all these algorithms that I've shown, they don't take the big picture into consideration. They don't do that. Okay, so the more we can plug in these different things together, we might be arriving at better learning algorithms. Fine. So now I think I'll end the class over here. Right, I will be sharing everything. I'll be sharing everything with everyone. I'll be ending the class over here and request everyone to go move into Google Classroom, because I'll be sharing a link for the quiz over there. And say if we start at 9:10, you have till 9:20 to finish the quiz and submit by 9:30. No more than 9:30, please, because I suppose 9:45 is your next class and you don't want to be late for that. Okay, I'll be sharing all the links with everyone. Please don't worry about that. Right. So I'll stop the class over here and I'll move on to excuse me, the quiz now. And if anyone has any more questions or queries or fine, I think we could do that. We could do that. But if you are solving a quiz, fine, we could keep it active. No problem. Fine. So I'll just stop sharing my screen and I'll stop sharing my screen and I'll just share the link to the quiz. We will finish submissions by 9:30. Right. So I suppose everyone, I just have shared, right, I have shared the link, and good luck to everyone. It's a very simple quiz. It's just kind of looking into what we did yesterday. So I'll mute, keep myself on mute, and if there are questions, I'll unmute myself. Okay, you have time till 9:30.